Alrighty. So once this decides to load, we're going to go ahead and start alkenes. There we go. So I'll put that up, and then we'll have a separate notes for the alkenes. Alrighty. So what chapter is this? 8, I think. So alkenes. Remember how to make them. So we saw that we could do E1 or E2, which are both elimination reactions, where we have a hydrogen and a leaving group. And we would have a base. Depending on the type of elimination, we would either form a carbocation or not, and we would end up making. I mean, I've got a cis one here, but we'd make the trans one too, maybe depending on. In this case, yeah, we would get the trans one probably primarily, and then we would have the cis one as a side product. But elimination is one, right? So we would typically use a base and some heat. We would choose the mechanism depending on our base and the solvent, right? So if you have an aprotic solvent, you're more likely to do E2. If you have a protic solvent, you're going to probably go through an E1 mechanism. So we want to keep those in mind. All right, so that's one way to do it. It's one way to make an alkene. We also kind of saw. Someone remind me. Did we talk about making alkenes this way to dehydrate an alcohol? I don't remember. If we haven't, I'll go over it real quick, and we'll go from there. So hopefully someone is out there watching. Probably not, though, because we know that nobody is going to pay attention because this is not on our next exam. So hold on, let me. Oh my god. Trying to just see here. Okay. Cool. Jackson's still here. So, did we cover this last part here where we dehydrate an alkene? I'm sorry, to make an alkene? If we didn't, okay, I'll just go through it because I don't remember if we did or not. Um, so let's take a look at the mechanism. Sulfuric acid. So I'm going to go ahead and grab a proton off. We now have a positively charged water, which is a good leaving group, remember. So it's going to go ahead and leave. Technically, we lose this. With that, we have a carbocation. And then our dear friend, the water, or actually, it's probably going to be the best thing that's here, is going to come in and grab the proton and eliminate, which will produce the H3O plus hydronium, which is which is what we would have in sulfuric acid anyway, right? So that's our bit there. Okay, so we're going to have a dehydration reaction, follows a kind of E1 mechanism, and we end up with an alkene. So it doesn't really matter. Again, I've put a cis one here, could be trans. There's no particular reason that we would have one or the other. In fact, the trans would probably be better because it's less sterics. So, but you'll get both. So the idea here is that's how we can make alkenes. Alkenes, sorry. We take one with a halogen or an alcohol, and then we can eliminate. Remember, we can also do an E2 elimination if we tosylate the alcohol, turn it into OTS if we tosylate it, and then we can eliminate it that way as well. So we have many different ways to eliminate. We can even do the E2. We can get it to go in the Hoffman product rather than the Zaitsev. But that's how we make alkenes, right? So that's kind of our main way of doing that we know so far. So let's see all the things that alkenes do. We're looking at addition reactions for this. And we're going to look at these very closely. We're going to see that if we take our alkene in the presence of some sort of hydrogen and halogen, we will end up putting them on different carbons, right? We're going to add to our pi bond. So we're adding a molecule alongside of it. And we're going to look at what that looks like. We've just seen as well that if we have HBr in the presence of a peroxide, we will end up getting the opposite. We'll end up putting our bromine on the other side of the molecule. What else can we do? We're going to see that we can put on halogens. We can put on hydroxy groups. We're going to see a couple of various ways to do this, but we can put on hydroxy groups, and those will either be syn or anti to each other. We can put on, and in fact, just for now, because I'm going to make it not chiral, so that we don't have to worry about syn and anti yet. We can put a hydroxy and a halogen on. What else do we have here? We can cleave them as well, but those aren't addition reactions. And then, of course, we can add just hydrogens to them, but that's kind of less. We're going to see that we can just add hydrogen, which is quite silly because that means we've now got a less reactive, less useful thing. So we have a lot of things we can do. And these are just the additions. So we're going to have other reactions besides additions later on. We're going to see we can add a halogen. We can add a halogen to either side. We can add two halogens. We can add some hydroxys. We can add a hydroxy and a halogen. And we can add some hydrogens. I don't think we need a single hydroxy. We've got a couple ways to do that as well. I'm going to just say, I'm going to leave it like this again. We have various reactions that will put a hydroxy on various different sides. We're going to see one to put it on more sub versus less sub. So these are some of the addition reactions. What else do we have? We can give them some. We can make epoxides. That's something we probably haven't heard yet. Epoxide. You can have things with carbines as well. Actually, let's not worry about the carbines now because those are a bit more specific. So let's just see what we can do with all of these things. So lots of things we can do with alkenes. They're very synthetically useful for us. We can do a lot of transformations. That's why this chapter tends to give students a lot of stress, because we're going to see we're going to have 14 reactions that we're going to want to know the mechanism for. We're going to want to know the regioselectivity for, the stereochemistry for. There's a lot of information here. So this is, after spectroscopy, this is going to be your next biggest pain. You thought eliminations and substitutions were bad. Fun stuff. Let's take a look at the first one here. Adding a halogen to our alkene. We're going to see that alkenes, by the way. Let's just look at this. Just due to resonance, alkenes. And I'm going to use this one for a lot of things. This basic alkene here, which looks really bad. Let me try that again. There we go. Here's an alkene. We're going to see that if this were to resonate, I just drew exactly the same thing, we would have a negative charge and a positive charge, right? And we'd have the lone pair there. And I'm going to just make that a little bit more pronounced. Of course, the resonance is not very likely, right? Because it's clearly destabilizing the molecule. But just due to this, we can see that we typically will have a little bit more electron density on the less substituted carbon and a little less electron density on the more substituted carbon. We remember that carbocations are stable with more substitution. And that carbanions are stable with less substitution. So it is unlikely we're going to get the other resonance where we put the negative charge on the tertiary carbon. That's less likely. So we're going to see it's just more likely that we're going to be able to substitute onto, we're going to be able to see that the kind of less substituted side is more nucleophilic, and the more substituted side is a little bit more electrophilic. So let's write that again. So this side is slightly nucleophilic, or dare I say, a little bit negative. This side is slightly, um, this is slightly, what's it? Electrophilic, which will be slightly positive. Again, we are looking at these, just, they're not really positive negative, but we're going to see that as a result of reacting them, we're going to preferentially choose one side over the other when we have non-symmetrical alkenes. And so, if this thing is going to go ahead and act as a nucleophile, let's say we're going to add HCl to this, we're going to see it's a two-step process where we are going to attack the hydrogen and kick out chlorine. So notice, by the way, these are two-headed arrows. Two pairs, or sorry, two electrons. So a pair is going on. So with this, we're going to see that we're going to make this new hydrogen. And in fact, I'm gonna draw this hydrogen as a special color, just so we see. I'm going to draw this hydrogen as dark blue. So we have now our hydrogen that's added. All right, because this thing has attacked, we now have only 3 bonds on the left carbon. We still have this plain old H. That H was here before. So we have a carbocation here now. Be aware, this carbocation can rearrange. As always, when carbocations are involved, beware of rearrangement. But it's already in the most stable position. So notice, by the way, that we've given 2 electrons to chlorine, so now we have chloride. And that is going to just come in and attack our positively charged carbon, leading to following product. So we've added one H and one Cl to our um, original molecule. That's what I wanted to say. So notice we started with a pi bond and a sigma bond, and we have made 2 new sigma bonds. So we broke a pi bond, that was the C double bond C, and we broke the HCl bond. We've also made some bonds with this. We have made a CH bond and a CCl bond. So remember, making sigma bonds is better than making pi bonds. Pi bonds have higher energy. And so we're going to see that even if without looking at the numbers for this, just looking at the types of bonds being formed, we broke up pi and a sigma and we made 2 sigma. So overall, we are losing 1 pi and making 1 sigma. That's energetically favorable. If you really want to look at the thermodynamics, take a look at the book. It goes through all the thermodynamics, all the fun stuff. Suffice it to say, this is energetically favorable. That's the end of it. We don't need to worry about it too much. So this thing happens. And it's going to happen such that we get what's called the Markovnikov product. This is the Markovnikov rule, is that when doing additions to pi bonds, or what's the best way to say this? I can say it in a very nice. No, I shouldn't say that. Um, Suffice it to say that if we consider hydrogen as the currency of chemistry, of OChem, the rich get richer. It is the quintessential American reaction. The rich get richer and the poor stay poor. Um, so, what we notice with this is, I'm going to draw it out again. Notice this side of the alkene has 1 hydrogen, the other side, the left side, has 0 hydrogen. This one is the richer one. And so it is where our other hydrogen will go. If we're following the Markovnikov rule, the hydrogen rich side gets more hydrogens. It gets richer. And so in our product, notice that that same carbon got richer. If this were a nice equitable universe, it would be so lovely to have them be of equal wealth. But no, it is reality. Capitalist America, rich get richer. So the one that has the most hydrogen will get more hydrogen. So if one has two, the other has one, the one that has two gets the other one. All right, and the reason for this is, economics aside, the carbocation that's formed on more stable position. We can say it in that terms, right? So it's a nice mnemonic. The rich get richer. Whoever has the most hydrogens gets more hydrogens when we're looking at additions to alkenes. But if you want to think about this chemically speaking, it's because if we react that side, we end up with the carbocation on the more stable position. And if we react to the other side, then we're just going to hydride shift anyway. So we're going to still end up moving the hydrogen over. So even if we do react in the other spot. So the reason for that is we're going to end up forming the carbocation on the more stable position. So suffice it to say, again, we end up putting our halogen on the more substituted position. This is a Markovnikov hydrohalogenation. So we're adding a hydrogen and a halogen to our molecule. That's not a T-butyl or anything, that's an X. X is halogens, right? We saw earlier that in the presence of peroxide, hydrobromic acid or hydrogen bromide will actually give us the opposite product. We put the H on the H side. This is an anti-Markovnikov. Uh, hydrohalogenation. So we end up with the product on the other side, the less substituted side. So the hydrogen went to the hydrogen side, the bromine went to the other side in our Markovnikov example. However, in the presence of the peroxides, HBr will add the opposite way. It will add the bromine to the less substituted side and the hydrogen to the poor side. So anti-Markovnikov, the poor get rich. Right? Markovnikov, the rich get richer, assuming that hydrogens are the currency. So Markovnikov, the rich get richer. And I'm going to say that I'll just make this a little bit more consistent. So we end up with our bromine on different positions. This is called Re-Geochemistry, where the reaction takes place. And notice, by the way, we end up with, for the bottom one, we do end up with the chiral product, so we would need to say plus minus and all that good stuff. It's a radical process, so there is no preference for one over the other. We are going to see sometimes we will have stereochemical outcomes that are relevant as well. But for this one, it's just racemic. So we're going to see that the Markovnikov rules will guide us towards which product we get. We'll either get the Markovnikov product, where we will add our hydrogen to the hydrogen-rich side, or the anti-Markovnikov. And this is for hydrohalogenation. We're going to see sometimes we're going to get it on both carbons, so there is no Markovnikov. But sometimes there is. So that's our first kind of idea. So we are going to go ahead and add to that position. All right. Let's see here. Don't forget, remember with. Actually, this is a good idea. Let's do this. There's a problem here I wanted to do. Aha. Okay, let's look at this one. All right. Let's add HBr to this guy. Or let's use HCl. You can use HCl, not a problem. So this is going to be this is a Markovnikov addition, right? We do not have peroxides in HBr. So that's the unfortunate thing with this. You're going to have to learn which reagents go which way. So just old HCl or just old HBr without the peroxides will go Markovnikov. This is a Markovnikov addition. So that tells us that we're going to attack the hydrogen onto our richer side, which means it's going to go on the left for this particular one. So if it goes on the left, we now have 3 hydrogens there. Notice this carbon in the middle has only 3 bonds. We have a rearrangement now. Secondary carbocation next to tertiary one. That is prime time for a hydride shift, right? We love our hydride shifts. So, without putting all those hydrogens, I'm just going to omit them, but we now have our carbocation on the tertiary position. Remember, carbocations will always rearrange to make themselves as stable as possible. So we now have 2 hydrogens there, and we have still the 3 on that carbon. So we've moved a hydrogen over. And so now our bromide, I'm sorry, I used chlorine, didn't I? Don't forget we lost that technically here. Here it is. It's going to come in and just add on. And so this is still a Markovnikov addition, but we had a rearrangement happen. So this is our product. So you might be tempted to just throw, Markovnikov, I'm going to just put the H on the less substituted side. I'm going to put the chlorine on the more substituted side. Well, maybe not so easy. And apparently, if we were to just do that, this is about 60%. You don't need to know these, but this is just throwing some reality in here. That yes, you get both, right? Because when carbocations enter the scene, they will try to do things. All right, maybe they're not going to be successful all the time. But we see it definitely takes place because we have 60% of our product distribution being the migrated, the rearranged structure, right? So we do have to consider this as well. Okay, so always keep in mind the possibility for rearrangements whenever you have a carbocation happening. And for just to put a blanket out there, if you have a carbocation that can rearrange, you should. That's going to be the predominant product. All right, again, yes, you get multiple, but the predominant one will be the rearranged one. So here's in big letters. Always rearrange to a more stable position before nucleophilic attack. All right. right, so the major product is the one that rearranged. All right, so you will still want to do that. So we've added a hydrogen to our terminal carbon there, the end carbon, and now we've added the chlorine one more carbon away. So really we added with this, we added the hydrogen to the end. That's going to happen in both cases. And so we end up with the chlorine on various spots depending on if it rearranged or not. And how do we know this happens? Well, we can label it isotopically because we're going to see that if we take this and put it with deuterium chloride, we end up with the deuterium on that position. And yes, we will technically end up with some of it here. Remember, deuterium is just hydrogen, an isotope of hydrogen. Hydrogen with a neutron. So remember, the deuterium acts like hydrogen. As it is, but we can identify it. How do we identify it, by the way? NMR. Very easy to tell in NMR where your deuterium is, right? Because we would only see two hydrogens at the end there, and so we know how to distinguish between these two molecules very easily, right? And remember, deuterium is going to split things differently, or it's not going to participate in the same way that hydrogen does in NMR. So there are easy ways to tell where it's gone. All right, same thing with where the chlorine ends up. Very easy in NMR to tell. For example, we have an isopropyl group, we'll see a septet, and actually it'll be more than a septet, it'll be an octet, and a doublet worth 6. Very easy to tell. Versus in the first one, we're not going to have that octet at all. No octet here. No octet here. We will have the octet in NMR. Right? So there is a reason for studying NMR, right? We're going to have this H here that's going to show up as an octet. Right? There's 7 neighboring hydrogens, so it will see an octet. We will have no octet in the other molecule. These guys will be singlets, in fact. This would be a doublet. Right? So we have all sorts of NMR reasons to be able to tell what's happening with this. Wouldn't that be so fun, by the way, if I'm like, here's your product in the NMR, like, figure it out. That'd be so fun. So, good stuff. Good stuff. Alrighty, so don't forget all that fun stuff either. All right, that's still going to be very, very relevant. How do we know what product we get? NMR. That's how. Right? There is a purpose for all this stuff. All right. So, do another one. All right. So, let's see what else we can do with alkenes. We have the opposite process of the dehydration. You need water with this. Really H plus. In fact, I'm going to just say H3O plus H2O. So water with acid. You will end up with adding water to your double bond. Just like we added HCl, we can add H2O as well, or HOH. And this is a Markovnikov process. It's a Markovnikov hydroxylation with a carbocation mechanism. We're going to see there's another way to do a Markovnikov hydroxylation that's going to end up without a carbocation. And that can be beneficial, right? Because with carbocations, look, we had rearrangements happen. If our mechanism does not have a carbocation, there is no possibility for rearrangement. So it depends. If you don't care about rearrangements, this is a great way to do it. Acidic water, boom, done. Yes, Markovnikov puts your thing on the most substituted. So notice we have a tertiary alcohol. The anti-Markovnikov one would be this, which is a secondary alcohol. This is anti-Markovnikov. And so we'll see reagents to do that as well. So yeah, Markovnikov is the more substituted side, gets your substituent. The rich side, the side that has more hydrogens, gets more hydrogens. So notice again, we have one hydrogen here, we have two hydrogens here. Ooh, Hoffman is a double bond that's formed. So Hoffman and Zaitsev are double bonds that are being formed. Markovnikov is getting rid of double bonds and putting something else there. So Markovnikov is for addition reactions. Hoffman and Zaitsev are for elimination reactions, the opposite of these. Okay, so they are related, but kind of opposites. All right, so suffice to say, we're just going to take a look at this mechanism, and then we'll end for the day, and then we'll go from there. Okay, so how this is going to work is we're going to do the same thing as before. We're going to go ahead and have our lovely alkene. We have our acidic species, good electrophile. Remember, we are doing this Markovnikov style, so our hydrogen-rich side gets the hydrogen. Whichever side has more hydrogens gets another one. So by doing this, we now have a second hydrogen on our thing. Water's our byproduct. Lo and behold, the water comes in for round two. X the electrophile. Remember, rearrangements are possible. We have a carbocation. Not necessary in this case because it's already tertiary, but just be aware of that. You can get migration to happen. So once this attacks, we now have water stuck on there. And then the last step, another water molecule comes along, and it's going to deprotonate this thing for us, thereby leading to the product. And again, I'm putting the H's just so we see that that's the Markovnikov rule. The rich get richer. The one that had the hydrogen gets more hydrogen. We are adding the OH to the more substituted side. We are adding the H to the less substituted side. So we end up with a Markovnikov hydroxylation here, right, with a carbocation intermediate, which means, again, rearrangements are possible. So be aware of that. All right, so that is our mechanism. I'm going to make it vertical for a sec so y'all can see. wonder if I can just make this. No, that doesn't work. Probably make it better here though. Well, whatever. That's the idea here. So we're going to be attacking the hydronium, forming our carbocation, which may or may not rearrange. Nucleophilic attack by water, deprotonation by another water molecule. Notice we get our H3O plus back out again as a side product. That is our catalyst, right? This is a catalyzed process. And so as a result, we end up with the anti-Markovnikov product. I'm sorry, Markovnikov. This is totally Markovnikov. Anti will be next time we look at that. All right, so that's all for today. I'm gonna make this horizontal again. So just keep going with these. I've already put your stuff up for the exam. I'll put some radical problems on. I don't know if I'm going to make it an actual homework or if I'm just going to just give it to you with the answers. I have to decide that. So, but I'll decide today. All right. So 2 weeks for your next exam. Spectroscopy. Do not forget it. There's plenty of problems. I know Kevin just dumped a whole bunch of his work into Discord. I would take a look, see if you agree or disagree with it after you've done it yourself, though. Still very useful to try it yourself. And then, since we have so much time, very good idea to do them now, this week, go through all 25 problems, forget about it for a week, then do them all again in a different order or something. And so, practice, practice, practice. Spectroscopy takes practice. That's all it takes. Figure out your fragments and then figure out how to put them together. And that's really all it is, but it needs a lot of practice. So don't forget. Because if you just see the spectra and you're like, what do I do? You know, it's very hard to give partial credit on spectroscopy if you have no idea what you're doing. So, if you can at least label peaks and make some fragments, you can at least get partial credit. So, all right. Well, that's that for today. This will be our kind of second one. So I'll put them both on YouTube. Remember, this alkene stuff is not for exam 3, it's for exam 4. So we're going to keep this one separate. All right. That's that then. We will continue on Wednesday. All right. Enjoy the rest of your day.